to the Latin America Regional Advisory Committee's technical webinar series, Recent Advances and the Road Ahead. Anna Curcio, Chair of the SEG Latin America Regional Advisory Committee, and myself, Lori Weitzel, will serve as your host for today's webinar. Before we begin, the model for this webinar will be a presentation followed by an extended question and answer session. During the question and answer session, please place your questions in the question and answer box. Please don't put it in the chat box. Peter Ike received a master's in geophysics from the University of Utah in 1989 and a bachelor's of science in geology from Michigan Technological University in 1987. He joined Conoco in 1990 in the United States and has worked as an explorer and potential fields interpreter in the Gulf of Mexico, Alaska, Rocky Mountains, and the Permian Basin. He switched from explorer to seismic acquisition coordinator early in his career from Conoco and later ConocoPhillips. As principal acquisition geophysicist in the Geophysical Operations Group, he worked over 25 years designing and acquiring borehole, marine, and land 3D and 2D seismic surveys worldwide. He's an active researcher and is the named inventor of over 60 U.S. patents. He left ConocoPhillips in 2015 and started Serenity Geophysical Consultants, focusing on shear wave and high resolution seismic exploration projects. In 2017, he joined In-Depth Compressive Seismic to help promote their technology. Currently, he is the CCO for Inter-Depth Compressive Seismic. Mr. Ike is a licensed professional geophysicist, continuing education instructor for the SEG, and an active member of the SEG, IAMG, GSH, AAPG, and HGS. So without further ado, let's please welcome Peter Ike.
Thank you. We'll get right started on this, and we're going to be giving you an introduction to compressive seismic technologies. We'll be going over the background, concepts, reconstruction techniques, some of the limitations of the techniques, and then I'm going to describe applications and examples of the technique. Now, I like starting with this particular slide deck because it points out that this technology has been around a while. This is from the Wired magazine in March of 2010. So it's now over 10 years ago this article came out. And what they were presenting was the concept that if you strategically undersample your image in the proper manner, you can then go through and using L1 minimization, slowly reconstruct the image a step at a time and build in the final results. So by strategically undersampling it, and that's where the science is, you can actually reconstruct the result. And this technology has been around since 2010. For example, in the what I would call the advanced aficionado magazines like Wired. Now, what does this have to do with seismic? What is compressive seismic? Basically, compressive seismic means that we're going to apply those compressing sensing techniques to the application of acquisition and processing. So we would go and acquire this type of design in the field. Notice I'm following industry convention of red sources and blue receivers. And you can see it's strategically not uniformly sampled. We run it through the reconstruction and we output this uniform grid. So we follow that same concept we just showed you. So what is compressive seismic really? It's this elemental concept that you should not intentionally sample your data in a manner that promotes coherent aliasing. And so what you don't want to do is intentionally put noise in your data set. So the bottom line is if you're going to go violate the Nyquist-Shannon rules, you need to be smart about it. And that's what compressive seismic really is. So where did this technology start? It came in really actually through medical imaging, because the medical imaging folks really wanted to understand how we could get a really accurate image in the body for surgeries and things like that. So it had to be accurate, it had to be amplitude preserving, it had to be fast. And this then advanced and was applied in digital photography. It was later taken into the seismic acquisition realm by Donahoe and Candace in the 2004 range, but it was really pushed forward by Herman and Hennefert in 2006 to 2010, Zwarte and Saatchi, Zagadeth and Saatchi, etc. You know, there's been a lot of active people working on this technology over the last, 15 years in the seismic industry. So that's me, as you probably can tell. If you're the guy going into that machine, you want it accurate, you want it amplitude preserving, you don't want any errors in it, because if they're planning on doing surgery to you, you don't want to deal with a fuzzy image. And that's where CSR technology comes into it. So what's the state of the industry? The industry as a whole has been very active in this. There was a August 2017 leading edge special section. 2018 SEG was showed some of the applications. 2019 distinguished lecture, we had Felix Herman do a great talks out on the CS technique and 4D. 2020 is shaping up to be a really interesting SEG. I expect that there's going to be a lot of really good papers on it. So the technology is active, it's developing, and it's progressing forward quickly. So what's the value proposition to you guys? The whole idea here is we can do simultaneous shooting, so you can deblend in the CS-friendly mode. It gives you higher fold, typically 4 times the fold, so you get better quality. You get a better wavefield reconstruction. There's more flexibility of dealing with no permits and logistical issues, better processing, and we will show you that we think it replaces basically 5D regularization. So let's go through some of the concepts. And I'll start with just terminology, because this is a terminology, new technique to people. When I refer to compressive seismic reconstruction, that's my overall concept for CS technology. That's made up of 2 main parts. There's the CSA portion, the acquisition portion, and the CSP, which is the processing. I like to draw the line right here and say, look, anything that happens before the data put on tape, that's CSA. Anything that happens after the data's been recorded, that's CSP, which is essentially the processing. So let's go to the classic paper, and I'll give full credit to Herman and Hennefeld for this excellent discussion back in 2008, which really lays it out. The whole concept of CS is that when we regularly sample data, if we honor the Nyquist-Shannon sampling rates, we can take 3 cosine waves, we do an FK of it, and they come out as these 3 nice peaks, very cleanly, very nicely sampled, everything's happy. This is what we would like to do, but we can never afford to do it, frankly. So what we do as an industry is we go out and we regularly undersample the image, and we don't acquire enough data. We all know we do it, we design around it, but we expect that this is what we can acquire. So we design based upon what we can afford, not what we really want. Now when you regularly undersample these 3 cosine functions and you do an FK, okay, which one's the real data and which one's the coherently aliased data? That coherently aliased energy hurts your migration, it hurts your statics, it hurts everything you do, because it ends in this data you can't really tell whether it's real or it's noise. So what Herman and Hennefeld pointed out and say, if you use CS techniques and you randomly jitter and undersample it, you can now afford to acquire the data. So now we're non-uniformly sampling the result, and when you do the non-uniform sample and you do your FK transform of it, all of that non-uniformity and aliasing becomes this background fuzz, I like to call it, or noise. It's incoherent energy that has minimal application. And now your 3 peaks that you were after pop right up above the background noise. That's the concept in a nutshell. Don't intentionally put in coherently aliased data or noise into your data set. So how do you do this? The first generation technique is kind of this optimized or optimal jitter undersampling. Again, we're following Herman and Hennefeld's 2008 paper. So, you know, this technique's running around 12 years now, at least. And basically they offset and do this sort of jittering back and forth the sample spacing. You know, this works well. There's no complaints. It's been in active use for 12 years. You know, a 3rd generation technique, which is what we were using at the time, is optimized projection matrix. Now, I'm not going to go through and explain the math. I just want you guys to get a flavor for there is a ton of math behind how all this works. You know, it's very advanced. I freely admit I can't explain it. I am not a mathematician, but I work with a bunch of people who tell me this is how it works. The whole point of it is what you're trying to do is essentially get the gram matrix as close to unity as possible. And so that's the real nuts of the problem that you're trying to get to. So the point of this, when you get to it, the first and second generation techniques were not really optimized. You know, if you look at it, this is a first generation technique using random, gets you about 32 dB. By the way, my daughter works at SeaWorld, so you'll see a bunch of SeaWorld pictures. If you use sort of a recovery using an optimized sampling where you tune what you sample to the reconstruction operator, you can pick up 3 dB, and this is what we called our third generation technique. We essentially set up our sampling matrix so it knew that we were going to reconstruct it using an epochs type solution. Now, I would tell you today we're on our 5th generation technique. It's in production testing now, and we're starting to use it routinely on client data. And we'll show you what those improvements are. Because what we're trying to get to is this image. We're not there yet. We freely admit it. We cannot reconstruct every one of those little water droplets yet. We're getting close though. And that's the whole point of why I say this is an active research project and there's a lot of work going on. Now, I mentioned these other solvers, or the solvers for the gram matrix. We're using epochs. Some of the common ones out there are ADM, ALFT, MWNI is very common. These all have their pros and cons. They're different solvers. They have there's advantages and disadvantages. But I was sitting in the 2017 SCG when Tao was giving his talk introducing epochs to the industry, and some of the most famous people in the industry, who I can't quote them here, give who they are, were sitting right in front of me. They didn't know who I was, but I certainly knew who they were. And they were talking among themselves while Tao was giving his talk, and they made this comment and said that it's really more important how you implement the algorithm than the actual technique. But fundamentally, epochs works really well for geophysical works because it's FK based. So that was kind of a neat little comment on epochs. Now, I'll point out there's flavors of compressed seismic. Flavors is my particular term for it. We've been discussing the randomized or jittered or optimally adjusted flavor. There's a lot of big industry oil companies that use this technique. They tend to use ADM as their solver. They tend to have small random shifts, and they tend to follow Herman and Hennefert's work. We, on the other hand, at In-Depth Compressive, we use what's called regular indexing. Regular indexing uses POX or epochs, and we tend to have large shifts. We do everything on a regular grid, and we're following basically Zuarti and Sachi's papers and Zagadev and Sachi's papers. The nice thing about this regular indexing is it works particularly well for the crew, so it's easily to implement. Now, what's interesting in the 2020 SCG is people have started blending these two techniques. So they're actually using regular indexing and randomized or optimally adjusted on top of it. And I think you'll see several papers at this SCG discussing how this works. And so we don't know if this is going to be the wave of the future or just a variation on a theme, but it's interesting to see how the flavors have now become a triad instead of a duology. So let's talk about regular indexing because we've already mentioned the randomized approach. What Nyquist and Sachi showed from their 2010 papers, if you want the nice uniform sampling, you do an FLK of it, you get a single spike. As you sparsen up, you get more and more spikes. And they said, okay, your goal is to achieve the top with less samples. They pointed out basically you want to get is your single spike up here and your background fuzz, if you remember your sampling, to be as low as possible. And there's many different solutions. It's a family of solutions that work. You just have to try to pick the best one. If you extend that from 1D to 2D, it's the same concept. You want the uniform groove sampling, do the FKK, you get a spike. As you sparsen things up over here, you get the single spike in your background gray. Your goal is to try to make this as white as possible with as few samples as possible. As you get fewer and fewer samplings, you end up getting more and more background coming up, and that's basically your error function. So we'll show you that in more detail in just a bit. So let's talk about an industry standard layout. This is sources as red, receivers in blue. This would be a very traditional layout for the industry. 50-meter shots, 350-meter lines, 50-meter receivers, 300-meter lines. Very conventional design. If we look at the random or dithered approach, the alternative flavor, you can see that this is an actual example of what their survey would look like. It's very reasonable. It's easy to implement. You can see you've got a lot of shifts in there. If you overlay it on top of conventional, you can see there's all these little small shifts. That's the jittering. And so there's a certain level of randomness that this technique needs to work, is my understanding of it. If you go to the regular indexing of method, this is the regular index solution that we use. You notice there's big gaps and everything's very grainy or gridded. This also gives you a good reasonable layout. When you overlay it on conventional, you notice that it stays right in this grid type solution and everything lands on a grid node. And so that's the real difference between the two techniques. One is more randomized, one is very gridded. Regular indexing does not require randomness to work. Now, either one, once you go through it through reconstruction, you're going to get something similar to this. It's going to be this somewhat of this regular uniform grid that you've recovered. Now, the actual details depend on the technique. Neither one's right, neither one's wrong. It's just how you do it. You get something like this. Now, if you shoot this out with a conventional design on 12.5 meter bends, you get about 150 fold. If you shoot it out on 25 meter bends, you get uniform fold. You get 600 fold at the 25 meter bends. And so one of the beauties of CS technology is that using the same equipment, I can deliver the same fold on half the bend size, or I can give you 4 times the fold on the same bend size that you would have used conventionally. The neat thing about it is you get to have the signal noise versus resolution case. You don't have to pick when the data is acquired. You get to make this decision when it's all the way down to processing, so you're not committed. And that's one of the real advantages of the technique for acquisition. So let's talk about this reconstruction we've mentioned. You know, essentially, CS is this non-uniform sample data. And what we want typically for processing is a regular sample data set. This process is the reconstruction technique. And so when we talk about a reconstruction, all we're doing is taking the non-uniformity and taking it to a more uniform result. So what does this look like? Here's an example of an actual real shot record from the Permian Basin. And so this is an example before reconstruction. You can see the gaps in the non-uniformity. That's what it looks like after reconstruction. So I will go back and forth on this a few times just to show you. So here's the before. This is what you feed into the reconstruction algorithm. This is what you get out. And you can see it does an excellent job filling in all those details. And you notice in the shot records here that it's no longer the non-uniform spacing that you can see here. You can see the non-uniformity. The reconstruction fills it in. If we take it to another example, this is one where you can see definitely the reconstruction gaps in the coverage. There's after reconstruction, it fills it in. So here's the before, and this is after you reconstruction. So that's what the reconstruction provides for you, is this fully populated data set. This is from Tao Zhang's 2018 paper. So let's talk about the limitations of this technique. Like everything, you know, there are limitations. We wanted to test what the limits were on something that was very publicly available and understood. So we used the SEAM2 data set, which you can get from the SEG. And this is representative of a Permian Basin 3D seismic data set. And what we did is we studied the case of a 50% drop of live traces. We want to get 50% of the data out. Let's see how we did. And what we're going to do is show you the test. We now call these drop and reconstruction tests, because we recommend that you run them. Essentially take a densely sampled survey, drop the stations based upon CS, reconstruct and compare the results. So let's see what it looks like. So here's your nice SEAM data set. This is a mid-offset, and trust me, I have hundreds of these plots, but I just picked a few. Here is what you would do. Now this is the CS subsampled version of the prior plot. And so these are following the rules. This definitely shows you the non-uniformity and how many traces and where the gaps are. You run it through reconstruction, fills everything nicely in, and then of course you want to compare it back to the original. And there's your difference plot. So that's the amount of error, and this was in our Gen 3 technology still, so this is generation 3. That was the amount of error we had. Let's take it to a time slice. And again, this is from Tao Zhang's 2019 SEG paper. Here's a 2-second time slice. Here's the 50% reduction in CS. It doesn't, you can see how it changed everything. Here's the reconstruction. You notice that's a pretty complicated wavefield from seeing. There's your error function. So we can reconstruct to a 50% trace level with that sort of error function. So you can actually put this in terms of numbers. That's one of the nice things of the drop and reconstruct test is we can quantify the error. And so if you look at it and say over the 1 to 2 second range, we're down about, our error is down about 40 dB, and this was in Gen 3 technology. Typically in the real world though, when we do drop and reconstruct tests, we see 25 to 35 dB down differences because reconstruction reconstructs coherent signals. It does not do a good job on random noise like wind noise. And so what you really end up measuring, frankly, is how much random noise there is in your data set, because your reconstruction actually, with our technology, is in the 40 dB down range. So what are the practical limits of this technology? Because there has to be some practical. How far can you go and really get away with it? Let's continue testing with SEAM. Again, thank you to the SEG for doing the SEAM 2. Let's take a look at what happens, and we were just discussing the 50% case. So we wanted to get rid of 50% of the traces. Let's look at 25, 9, and 4%. At this level, everything looks pretty reasonable. You can go down to 4% of your actual data acquired in the field and reconstruct a nice result. And so instead of having, 100 sources and receivers, you only had 4 sources and receivers, and you could reconstruct this result. And you go, that's amazing savings. Well, what happens if we start actually looking at the difference plots? So when you compare the reconstruction, doing a drop and reconstruct test, you can see that 50%, the error function is really nice. There's almost no loss of fidelity. 25%, okay, you can start to see you're leaking some. By the time you get down to 9 or 4%, okay, you've lost a lot of significant information, so that's quite problematic. Let's put those in terms of numbers again. If you look at it and say for the 50%, here we were just under 38 dB was our signal noise ratio on the drop and reconstruct. If we went to 25%, we were just under, say, 28 dB. But by 9%, you're only 14, and 4%, you're only 5 dB down. Okay, that's noticeable loss. And so our rules of thumb is basically 50% is safe, 30% is concerning, 25% is, you better have really good data, and I don't suggest you do it, frankly. What about different operators? Here's an example of different size operators. And the real point of this is you get out to some of the conventional acquisition like 50 by 50 or 165 foot by 165. Your error function is in like the 2 dB down range. It's really quite poor. And so this is what you see. If you take an FK of this, our conventional spacing at 165 foot or 50 meter is highly aliased. You have all this alias noise into your data, which is going to come in coherently and cause you a great deal of grief. And I'm sure you've heard people in the industry say, well, just acquire it at 82.5 or 25 meters. You're still highly aliased. You really need to get down to this 12.5 or 6.25 meter spacing to get out of the alias zone. One of the neat things that CS can do, if you remember, is if you're willing to pay for a 25 meter data set, I can give you the same fold and same sampling 1 step finer. So I can take it to 12.5. So that's the advantages of that CS technique, is you can acquire this in the field in CS mode, and I can deliver you 12.5 meter data unaliased on the other side, which is really a neat trick. Or if you can afford 12.5, I can give you 6.25. So if you look at this in terms of your sampling operator, you can see that, if you're at the 6.25 meter, your difference function is trivial. 12.5, you can live with it. 25 meter, you're leaking a lot of energy. And by 50 meters, or 165 foot group intervals, you're definitely got an alias problem. You're leaking a lot of energy out there. So the conclusions is 50% reduction is great. 30%, I wouldn't go below it unless you had spectacular data. And this CS technology allows you to basically address this aliasing by moving down 1 step in your resolution chain. So what about ground roll suppression? You know, if you can move this down one step, then you ought to be able to attack the ground roll. This is from Tao Zhang's 2019 paper. So let's do a drop-in recon test and test this. So what the proposal is basically normally you'd have your full processing flow through PSTM. And what we do if we're doing a drop and reconstruct is we would do the CS subsampling here. That's the drop step. Process it through, we reconstruct, and we would compare these two. That's how you get your drop and reconstruct step. What we came up with the help of our industry partner was what we should do is actually immediately after we drop, do a instantaneous just reconstruct it. So you get rid of the traces, you do a field reconstruction, you process it, you throw out those traces again right here, come down, and then you reconstruct it again. So essentially multiple passes of recon versus a single pass of recon. And here's the result of that. So here's the recon test showing these different passes. And if you look at an early shot record and all this, you go, you know, I don't really see a great deal of difference in this. The difference was, and this again was our Gen 3 technology, is you can see here's the full data set, here's the second drop with the early reconstruction. It's really essentially no difference all the way up to the very shallowest. You notice we do have differences here. This is where the Gen 4 and Gen 5 technology came in, is we've improved that to the point that these two are now virtually identical in the shallowest type reflectors. And so that's where we've been focusing on, is to get from the grassroots to the bottom all the way reconstructed accurately. So let's show you some examples of the reconstruction workflows, because there are differences in the industry that are out there. You've got CS-Recon, which we've been talking about. That's when you do it on a particularly designed survey for CS. So you go into it knowing you're going to shoot a CS survey. And then we have we call the epochs recon, which is a workflow for just conventional data, meaning you didn't design it for CS, but you're interested in trying to apply these techniques. So essentially you can think of epochs recon or conventional recon being applied to any survey not specifically for CS. And then CS-Recon is anything designed for CS. So you just have these two different workflows in the industry. So how does epochs recon compare to 5D then? Because that's what you're essentially replacing is your 5D. We had a client come to us and basically want to do an independent blind comparison. And so what they did is they sent data out to a bunch of people in the industry and said, here's the flow, do it exactly like this, substitute in your algorithms and see how they do. So here's a 5D reconstruction from one of the major vendors in the industry. Can't say who because that's the rules, but guarantee you know who they are. They probably use them if you process data. Now, if you look at it, look at the skip here, look at the lack of continuity, notice the noise chaining down, notice the lack of character here, and notice these little differences. And say, okay, that's not a bad 5D reconstruction. Here's what epochs recon does. Notice we've pretty much healed that full skip. We have a lot better character here, and the details down here are fully through in the objective section. So I'll go back and I'll show you the 5D regularization, epochs recon. And so that's give you an example of how you could apply to conventional data. This was not designed for CS. This is just an off-the-shelf spec survey that was used as a test bed. And so the client company was interested enough in our improvement. They said, okay, we'd like you to do a different thing. We want to take as many other steps out of the process as possible. So we want you to do a brute stack using this velocity field. So here's our competitor's 5D regularization, just showing you as an example of what 5D are from a major processing company. Now, things to look for is look at the continuity in the data, look at the edge, termination faults. In particular, it's interesting is to notice the diffraction tails. You know, the 5D regularization did not put in the diffraction tails like you'd like. Here's epochs recon applied to it. You know, this CS technology, because it views data in a different way, basically put in those things like look at all the diffraction tails, look at the sharp edge, look at how it filled in the shallow objectives. You know, and going back to the 5D regularization, you notice the skip right where the laser pointer was versus the CS technology applied to this concept. And again, this was not a CS survey. We're just applying that concept to the data. So, you know, it has a lot of power for off-the-shelf data because you're just viewing it in a different realm than you would with conventional 5DR. What about older data? We get this question, say, what happens if you take an older data set? And let's take one from 1994. And so this was a conventional survey, obviously not tuned for CS back in 94. And what the client wanted to do is do the same thing. This is from Tao's 2017 SEG paper. So here you have the 5D, or the raw data. So there's what they were hunting. This is the 5D regularization. Now you notice when you look at it, the 5D regularization has a distinct grain to it in the data set. If you look at the epochs reconstruction applied to it, and again, that's for a non-CS based technique, you notice you've got this geologic grain coming through, and you can definitely see that there's a target developing right here on this shelf break. Now, what I've been told is this is a producing field and drill. This is from the Permian Basin, but it gives you an example of what that 5D reconstruction does right here versus a epochs reconstruction or CS-based technique on it. Now, CS reconstruction has different outputs in the industry. There's two different general trends or output products you can get. Basically, we call them down the line or regular grid. Other people may have different naming for it. But regular grid basically means you output on exactly what it says, a regular grid. This is good for RTM, beam migration, rock property attributes, things like that. That works really good on the regular grid. The other one is down the line. So if you're cross-line sampling, of course, you go for a down the line recon. And this one's really good for Kirchhoff migrations, picking faults, subtle structural things, because your reconstruction down the line is more accurate in theory than some of the beam or the regular grid results. So this is from TJ's paper in 2019. Showing you an actual result from the Permian Basin. So here's the raw input. Now this gives you an idea of how varied the actual acquisition is when you're looking at it in the field. This is the non-uniform result from the field. So here's the fully processed raw. Here's the down the line solution. So you can see how the reconstruction went right down the line. It gives you this result, very similar to the raw. And then on the bottom is the grid result, which you can see is quite different overall from the down the line or the raw data set. When you look over at the seismic data, it's really hard to tell much of a difference. And what we tell people and say, they're just different mathematical constructs of how you view the data. Neither one is right, neither one is wrong, neither one is better, neither one is worse. They're just two different ways of thinking about the problem. And so it's up to you guys as the interpreters to decide how you want to do it. Now, we would tell you that down the line is really good for Kirchhoff type migration and structural imaging. The grid is really good for Gaussian beam and RTM. You know, what are you going to do with the data? I would tell you most of the clients we work with are now requesting both. And my understanding is that's kind of the trend in the industry. So I was telling you that we were working on the shallow, trying to improve the reconstruction from shallow to deep. This is no reconstruction on a fast track cube. So you can see they had this shallow anomaly they were chasing. Here's the full processing, and you can see the results on it. And this is up in the very shallow, you know, there's 300 mils, so about 400 mils down, 450 mils down. So we're definitely working on trying to improve this. This is from TJ's paper in 2019. And so, you know, we're definitely getting there. So the technology can preserve the data up shallow. And then you have the question, of course, how does it do in the deep? Here's an example from the Permian Basin showing the deep structure. And you see that it's really actually quite nice imaging, shallow to deep, in an area that's not particularly known for good quality data. So this is at 800 milliseconds. And now I wanted to show you an example from the grassroots actual field record. So right there is the reconstruction up at the shallowest. This image should have been Gen 4 technology. And you can see we're imaging all the way down to 2.8 seconds. Very nicely imaged all the way through it. Good continuity, good character and everything. Here's the cross line showing you the structure. Here's this intrusive event. We're not really sure exactly what it is. What I was told is it might be a volcano down at around, what, 2.8 seconds. And yet you can see all the way up to the shallowest reflector. So, you know, the CS technology, I think we've proven up that it can work shallow to deep, works quite well, and no particular issue. And I remember when we first showed these slides to the client who gave us approval to show them, They said they suspected it was going to be there because of gravity and magnetics, but they've never seen it with any other technique, is what I remember from the discussion on it. So how does this actually work in the field, or how do we work with you? Now, I teach the land SEG seismic acquisition course. And so if you guys would like to learn more about how to design and acquire a 3D seismic survey, you know, sign up for it. It's an excellent course. I think so. And we use this book. So if you don't tell us how you want to handle your obstacles, we're going to use this book as guidance on how we handle things. Because if you understand what we're fighting with, we've talked about the fact that you need this non-uniform sampling. Remember, sources are red, receivers are blue. And what do you do if you have this lake? You know, CS sampling requires that we have a particular pattern. By the way, this lake is from northern Michigan. I used to go fishing and I caught some really nice fish right about here. And so I know it well, and that's why I picked this particular area. We wrote a program that basically does a regular index offsetting of the obstacles, but you could have done it by different means. And this shows you what the offset would do around it if you assume that you can't put any sources or receivers inside the lake. Now, this is not what I would call conventional offsetting like you would do for conventional uniform space seismic acquisition. So you got to wonder, how well did we do? You know, that's an interesting question. Well, what you can do is create what we call the mutual coherence map, and this shows you the mathematics behind it. This was from a 2018 SEG paper by Tao Zhang. And so what you end up with this is you get what we call the mutual coherence map. It's sort of like a fold map. And what you'd like to do is be in the blues and greens. Anywhere in the blues and greens are going to reconstruct nicely. Your concern is this yellow and red right here. And you can see right where I used to go fishing is a bad spot. You know, the nice thing about this is you now know you're going to have trouble reconstruct this. The south part of this lake, you know, you're not even going to know that you didn't have samples there. But right up in this region, you definitely got an issue. And the nice thing about this is you know it before you acquired the data. So we could go get a permit to put in pulled in receivers, or maybe get a little air gun out there and put in some extra shots to fill it in. But you can go and address it. So how does the CS compare to conventional seismic acquisition? Well, we insert the CSA step and insert a CSR step before we acquire and before we process the data. So let's take a look at how we would do a conventional CS survey, or a conventional survey and a CS survey, to reduce the cost. So we'll start with the laid out survey. By the way, Poggy Lake is right there. The first thing you do is you basically, let's get a permit, let's zoom down, let's take out the background. So we start with this stage, basically the seg P1 from the client or the design stage. In the conventional and the compressive, we start with the same thing. Now we're trying to save money here, so the question we ask the client is, what percentage are you willing to reduce the data? It's what do you want? You can go 0 to 50% in this terminology, and so let's use the 50% reduction. So we're going to get rid of 50% of the traces, so we run it through the CSA program and come up with the sampling. And this is what you sample. Now you can see it's very non-uniform. It's all on a regular index grid. It's following the work of Sachi and Nagade's basically paper. And we know this will work out nicely, but we should go check it. So let's go look at the mutual coherence plot. You can see it's all in the blues and greens, so we're going to be happy. It'll reconstruct well. And so this is what you would actually give your seismic acquisition contractor. In the CS case, you'd say, go acquire these source and receivers. In the conventional, you'd acquire this. Now, obviously, this takes more equipment. This takes more time because there's more shots than this. That's where we get this cost saving, is because basically you're not acquiring as much data in the field. Once the data come back from the field, you run it through reconstruction. Now remember, conventionally, we don't do anything. And in the CS mode, we have to reconstruct it. You then process it. You can process with whoever you like, but I particularly like this company for some reason. And then we hope that you basically, excuse me, go drill a nice successful well and move on. And so I think I've tried to lay out the case for you that compressive seismic technology is capable of reducing your costs. And we didn't really go into the deblending aspect, but you can deblend your data. We typically see 4 times improvement in the fold, so you get a higher quality data set. and that's the CSA part. You've got more flexibility for dealing with those no permits. Like I showed you with the lake, you can actually tune where you put your holes or your non-uniformity to fit their no permit zones. We feel you get better attribute processing with CS-Recon because basically we can give you that uniform grid of sources and receivers that nicely processes and goes into things like raw properties and attributes. I think I've made a reasonable case that CS-Recon type techniques basically do a better job than 5D regularization. So I want to say thank you to the committee. That was just a nice overview of CS, and I tell people and say it's like drinking from a fire hose to learn this technology. But the important thing to walk away from this is if you're going to go out and shoot a survey, you should be asking yourself, why am I coherently aliasing my noise and stacking in my data to make it more difficult to process out? If you go with CS techniques, you eliminate that noise source and your data will likely be better quality and cleaner. So with that, I turn it back over to you, Lori.
All right, thank you very much. I enjoyed your presentation quite a lot. If anybody has any questions, please place them in the question and answer box. In the meantime, I have a question.
Yes.
So for compressive sensing, do you think the industry is really ready for irregular sampling in acquisition?
It's actually fairly easy on the acquisition side to do the acquisition. It's more the issue you get in the field is numbering. You have to leave the gap to be able to reconstruct the tracing. That's probably the hardest thing, is to avoid ending up with station spacings that are 1001.5. So that's what you're trying to avoid. So you have to plan ahead your numbering, and that's probably the biggest issue. For processing, the companies who are messing around with this or working it have learned, just like we did, that you basically have to rewrite almost all of your processing programs to take into account this non-uniformity. There's a lot of what I would call intrinsically assumed uniformity built into algorithms. And so it's definitely one of those things that you can you have to take into account and learn. And we did over the period, and I know our other people doing this in the industry have slowly figured out these things also. Is you run it through a particular program, you have a problem with it. Let's see, can compressive sensing be applied to sparse OBNs? Or do you want me to type an answer or just tell it? Or
I think just tell it.
The answer is yes. Let's see, ConocoPhillips has published several papers on this. Frank Genoweski and Lori Williams, I think, were the authors on it. I didn't really go into that particular topic, but there's definitely papers out there by ConocoPhillips on this technology and using it with ocean bottom nodes.
Okay, I guess I have a follow-up question. Oh, there's one in the chat. We'll do the chat question first, and then I'll follow.
Okay, this technique has been applied to borehole seismic like walkaway versus VSPs and sparse VSPs. We have not. I believe, trying to think who did it. I want to say it was either Sinopec gave a paper on this at the 2018 or 2019 SEG, or it was a BGP. But there's a couple of papers applied on borehole work, as I remember it, that were presented at the SEG. We were working on one that we thought would go with a VSP, so I could give you a direct experience. But what we did is when we started modeling it, we realized it was not technically feasible, so we dropped the project. Can this technique be applied to other geophysical methods like EM? The honest answer is, I think yes, but we have not done it. We are actively working with a particular client. I'm working with them on a gravity type survey, and we're attempting to use CS techniques to reconstruct the gravity field. Now, should it work? The answer is yes. We don't see any particular reason, but does it work? I don't know yet. we're literally collecting the data as we speak. Let's see. When you are defined the final source and receiver location based upon pre-plot, do you use the Earth model or just based upon source or receiver pairs? Depending on the technique, some people do it with an Earth model, and some people do it with a layout source and receiver. We using what we call regular indexing. We use the pre-plot, pre-planned, where it was supposed to be from the very start. Everything starts essentially right at the first step of design phase, and whatever goes on in the field, just that's what happened. You know, it comes back as a grid. I know other people in the industry are taking that into account, and so they get a more tuned based upon the results. So you can either calculate that reconstruction grid based upon before, that's the regular indexing method, or you can do it afterwards. That's basically the other flavor method. Let's see, how does compressive sensing cope with noisy data, especially in the nears? Honestly, that's a lot of the art form of how you do it. Every company has its own unique approach. You've heard me refer to the different generations. The improvement in Gen 3 to Gen 4, excuse me, was essentially we are addressing that near trace data because that's what impacts your shallow. And the improvement from Gen 4 to Gen 5 was also addressing that near trace data. So that's how we approach it. It's difficult. I'll be blunt with you. How you deal with that shallowest information is hard. Let's see. Thank you for the talk. Let's see. Because irregular sampling needs individual receivers, not the cables or lines. However, in real acquisition, we use cables on land and sea most of the time. How feasible is this to do regular sampling? It comes down to your takeouts. If you have a regular uniform takeout cable, what you're going to end up having to do is make sure that whatever your irregular spacing doesn't exceed that distance, because you don't want to have it go too long and have to put in jumpers. So you're going to end up, no matter what, if you're doing cable, ending up with a pile of extra wire on the ground, basically, to get around this. Be honest with you, nodes work better for CS. I know of at least one job where the client company came back to us after considering it and said, you know, it's just easier to acquire the cable-based data because we have to walk that and we have all this cable anyway. And so they did it regular spacing. The argument you can make is that by going non-uniform spacing, like regular indexing or the other flavor of the dithered approach, you actually get cleaner results because you're breaking up that coherent aliased noise. And so I think that argument is starting to sway more and more people in the industry that you should really just acquire this stuff non-uniformly, even if you have cable. But it's a cost of information and an information aspect of it. So the honest answer is there is no right answer to your question. Let's be blunt about it. Okay, let's see. Nice example. I enjoyed the Permian stacks. I wish I could have shown you a bunch more. I didn't know how much time I had on them. It's impressive to see the improvement of quality. One of the things I didn't go into in this particular talk was the fact that when you do the CS sampling, I just mentioned it, when you reconstruct the data, your shot records end up cleaner. And that's because when you reconstruct those shot records, you don't reconstruct the random noise, you only reconstruct the coherent signal. So I'll give you a tip. If you're QCing data that's CS and you want to tell whether it's CS data or real data and you're looking at the reconstruction, look at the noise content of the data. You'll notice that reconstructed shot records are cleaner than the ones next to them that are what I would call real. So that's just a little tip to how you tell them apart. Otherwise, it's really difficult to tell recon records from real records. All right, let's see. Thank you for the talk, Peter. Because of irregular sampling needs individual receivers, not the cables or lines. However, the real, oh, I think we've answered that one. The top one. Let's see. CS techniques are the opposite with WHB, but WHB is popular now. can you tell me how to use CS versus, I honestly don't know what WHB is, so I apologize. I can't answer this question. WHB. You got me on that one. You'll have to explain what WHB is for me to answer it. So sorry on that one.
Okay.
On the CS guy.
Oh, wide
azimuth high density broadband. Again, I don't have a good answer for you on that one. I don't know enough about what they're doing, so I can't really answer that one. Excuse me.
Okay, I have a question. I was curious whether or not you and folks you work with have tried to apply AI, machine learning to this process.
We've got a couple of researchers who are experimenting and studying that because that's really one of the hot topics, but nothing that I've shown you was AI based. Every bit of this is straight algorithmically. Could it be applied? I think you'll see at the 2020 SEG, there's going to be a lot of papers where they basically show the AI being applied. I personally think AI has a lot of opportunities for improvement, but it's not my area of expertise.
Okay, thanks.
Let's see, have you compared field and recon shot records in FWI? I did not. One of our client companies did. And what they found is that we were fully AVO and AVA compliant, and it was they had absolutely no concerns about the ability to do wavefield interpretation or RAC attributes. We then had another client go and hire a third party to do the same analysis to our data because they wanted to have an independent verification that came back with the same result. I believe there was one, if not two papers in the 2019 SEG talking about wavefield reconstruction, FWI, and rock properties extraction from CS data. But off the top of my head, I can't quote the author. So try looking at the 2019 or 2018 SEG annual meetings. Let's see. Thanks, Peter. Great talk. Is there a proven potential of CS-Recon toward low frequency bandwidth samples on field examples? The answer is yes. It does a really nice job. I was not allowed to show that data. Sorry. But yeah, it works really well for that. It's kind of surprising. There's things about the CS technology that have surprised me over the years, and how well certain aspects come through have been interesting. The fact that you're reconstructing based upon the coherency of the signal versus the signal and noise is why you end up with some of these better results. So, I would also tell you we've done some work with engineering type data with this, 1/8 mil sampling, half meter station spacing. We've done a fair amount of that. Let's see, can we use CS for converter wave data? The answer is yes. In fact, some of the examples that were shown in this talk, I didn't make a point of it, which I apologize for, were 3C data. And we have done that. It does work. There's no particular reason why the CS technology can't apply to 3C. One of the critical questions with 3C is, do you want to do a field recon, meaning you do the reconstruction directly out of the field with no processing, or do you want to do shear static, shear noise attenuation, and then do recon? So, I would suggest if you're going to do it with 3C, you do it both ways. I see the advantage of having the higher trace density of the reconstructed data going into your shear statics could be a distinct advantage. We have not investigated that. That's just a personal opinion. So let's see, just thinking about it, I think there's the shear data, I guess I probably shouldn't say how many we've done on it, but there's definitely been a lot of shear work with CS.
Okay, thank you. I guess I have another question. If you were to talk with graduate students who are studying geophysics, and they found your talk interesting. Is there any particular coursework that might be most beneficial for understanding and developing this concept?
I'm not the best person to talk to that. There's like Herman, Felix Herman would be a better one because he's a college professor running these research consortiums. But I would tell you, if I were going back to school, what I would be taking is more math. I think a better understanding of advanced mathematical techniques, and particularly sparse matrix solutions, matrix linear mathematics would have benefited me. That's been a weakness in my whole career, is that I'm not very good at math. And so that would be my recommendation. It's really, you're trying to solve that Gram matrix, which is a very sparse, poorly populated data set.
Okay. All right.
And then the other advice I give you is, if you go back and you've seen my talk and you pull out your Dobrin or Telford or whatever college course book they're using for basic geophysics, and the first thing they talk about is, and now you lay out your stations at a nice uniform sample spacing. Question that point.
Okay. All right. Well, we have another. I think we
Let's see. Thanks, Peter. Nice talk. Do you have any experience applying CS in 2D surveys in mountainous areas with high elevation changes and high amplitude ground scattering? The answer is yes. CS works nicely under those applications. The best way to put it is, I wish I could have showed you examples, but that we don't have any to show. Now, I believe BGP gave 2 papers that are public in the SEG. One was 2019 and one I think was 2018, acquiring 2D data in Western China? Yeah, Western China, I think. I just remember them. They were 2D. But yes, does it work in 2D? Yes. Does it work in mountainous and difficult terrains? Yes. All those things are basically yes to all of them.
All right. We have time for maybe one more question. No? There we go.
Let's see. Nice talk, Peter. As we see the industry moving to smaller, cheaper, and more numerous survey receivers combined with denser SIME sourcing, where do you see CS playing a role in deliverables? Different megatrace densities still seem to be the mantra. Basically, what I would tell you is 2 things about CS in that mode. Is the CS technology allows you to basically step down 1 size in your sample spacing. So if you could afford 12.5 meter dense sampling, then I can give you 6.25 meter with CS techniques. And because I'm using the CS techniques, I'm not bringing in that coherently aliased ground roll into my data set, which you then have to get out. It's now removed as part of the CS acquisition. And frankly, if you go look at a lot of the high fold surveys that have been acquired over low fold areas, in particular basins of the world, what I find interesting is that you don't see this linear improvement in data quality. It's just, this is my observation with the higher fold, it's going up at a lower rate. I would argue part of that is because what they're doing is stacking in more and more coherently aliased ground roll or source generated noise that they're getting harder and harder to get out. And so I would argue if you had applied the same source and numbers of sources and receivers in a CS friendly fashion, you wouldn't do that, and you get a distinct uplift in data quality. And that's a test that frankly we honestly need to run, but who wants to go shoot a 30 square mile conventionally acquired high fold, high trace density 3D, and then go back and immediately go shoot it again with a CS type solution to prove that it works better. So let's see, CS processing versus CRS processing differences. I don't know what CRS processing is. CS processing is one of the things you have to take into account is the fact that there's a lot of intrinsic assumptions built into many of the algorithms which assume a semi-uniform or uniform spacing in terms of the source and receiver distribution. And so when you start feeding in non-uniform data, you have certain algorithms that basically fail and have to be rewritten. Let's see, can you tell me what's common reflection point processing. That's how I think all the data is being processed, is just a common reflection point. Essentially, we just do it straight imaging. So the processing is pretty conventional. You just have to recognize that the traditional algorithms that people have used to write certain programs need to be rethought in terms of the fact that now the station spacing is not uniform. And
Okay,
so that can be a problem.
All right, we have someone with their hand up, so I'm going to move Eberton to a place where hopefully he'll be able to ask his question to you directly. It should take a few seconds here.
So it will show up here, or is it going into some other place?
Oh, he should show up here. All right, and I'm gonna.
Oh, okay. I'd see it's showing up on the side.
I'm gonna try to unmute him or ask him to unmute himself. Eberton, can you unmute yourself? Apparently not. All right. Well, I'm not sure how to get him to be unmuted.
Well, while you're doing that, I'm just going to pass along. Thank you to everybody for putting up with my talk. I know I'm probably not the best speaker in the world, but yeah, I hope that you found this interesting and a valuable exercise. And I also want to thank the committee for putting this together. It was very nicely done.
All right. Well, it doesn't look like we're going to get him unmuted, so he just dashed. So sorry about that, Eberton. If you'd like to enter your question in the Q&A box, there's still an opportunity. And if not, and it looks like he's unmuted. So, all right. Eberton, please ask your question to Peter. Now he's muted. All right. He was unmuted and now he's muted. So I think we'll have to call it a day. And I'm very sorry about that, Eberton. But we are out of time. So with that, I'd like to thank you, Peter, for a great presentation. I'd like to thank everyone who has attended the SCG Latin America Regional Advisory Committee's webinar today. And please look for our social media posts to register for more interesting talks. Once again, thank you everybody for attending. Thank you, Peter, very much for your presentation. And so until next time, have a great day. So thank you.
Yep. I think you got one more Q&A come in.
Oh, all right.
Okay, just a general one. So thank you to everybody. I hope you guys enjoy it. And again, thank you to Lori and the committee for putting this together. It was very nicely done.
All right, thank you. All right, bye-bye.
Bye now.